So Mr. Korsmito's got both arms outstretched, creating a wingspan of 2 meters, and then he starts spinning around. And the dumbbells he's holding onto at each hand is going in uniform circular motion. Now, this 2 meters would actually be the diameter of the circle, and the radius would just be half of that, so 1 meter. The speed is given as 7.5 meters per second, and that's enough to get the centripetal acceleration right there. But they want us to find the centripetal force. And for force, we're going to just use Newton's second law. So we'll bring the mass into play here. The mass of each dumbbell is 2.5 kilograms. So for part A, the centripetal force, here, just draw a free body diagram here. So let's say here's a dumbbell. The dumbbell's got some gravity, and Mr. Korsmito's got to have part of his applied force, I'll call it FAY. Part of his applied force is holding up the dumbbell in the first place to balance out the gravity. And then another part of his applied force is going to be towards the center of the circle as he's spinning these around in uniform circular motion, because there needs to be a centripetal force here. So I'll call this his x component of his applied force, and that is the centripetal force. That is the net force as well. So the centripetal force, I'll call that FC. That's just the net force. And in this case, it's also just the x component of Mr. Korsmito's applied force. Okay, so let me say that it equals the net force. I want to write this because I know that the net force equals ma due to Newton's second law. And now centripetal acceleration is equal to v squared over r for uniform circular motion. So that derives the centripetal force. So I'll plug in the values. And get that in the calculator. Coming up with 141 newtons. All right, so that's the centripetal force. Now part B, what about the total applied force? The total applied force. Well, then we have to also take into account the y component, because he's also applying a little bit of force to keep it raised up at a level height, and that's going against gravity. So the y component of his applied force will equal the force of gravity in magnitude, which equals mg. So that'll be 2.5 kilograms times 9.8 newtons per kilogram. And let's see what we get there. 24.5 kilograms. So his total applied force can now be calculated by adding the x and y components, but not just adding the magnitudes, because one of them is in the horizontal direction, the other one's in the vertical direction. We have to add them with the vector addition. And we'll have to find out the hypotenuse here. And I'll get the angle as well. So this red line here, that represents his total applied force. Okay, so in terms of the magnitude, that's the Pythagorean theorem. It's given me It's giving me 143 newtons. We did 2 sig figs. And the angle will be the inverse tangent of opposite over adjacent. And that turns out to be 10 degrees. All right, so his total applied force is going to have to be 143 newtons. Now, if this direction is really complicated, which direction is his total applied force? Well, there's two things I have to say. First of all, it's towards the center of the circle, because we need that to happen for our uniform circular motion. And also 10 degrees above the horizontal to counteract that gravity.